I already talked about it for 3 days. Hopefully you guys know that by now. But yeah, so Ken, fortunately, has agreed to step in and do the keynote this morning. There will not be a Sky Talk today at our normally scheduled time, I think 1 o'clock. So you get a little bit longer time for lunch. But we absolutely have, it's a fantastic talk as well. So let me introduce Ken. So Ken got his bachelor's from Princeton in 1987 and then spent 5 years at Stanford getting his master's and PhD in electrical engineering. And Ken, I just realized we were at Stanford at the same time. I was an undergrad, he was a grad student. I don't know if we ran into each other, maybe so. But then he went to IBM T.J. Watson Research Center in '92, worked there for 5 years. And that's where he focused on design microprocessor methodologies. Since 1997, he became a professor at Columbia University. He's now the Lau Family Professor of Electrical Engineering and Biomedical Engineering. But Ken wasn't just an academic type. That's not his nature. He was also Chief Technology Officer of CADMOS Design Technology until Cadence, my current company, bought it in 2001. Currently co-founder and board chairman of Ferric Inc., which is commercializing technologies for integrated voltage regulators and quicksilver blow systems. I'm saying this right?
Biosystems, yes.
Oh, biosystems. It's an I. Oh, it's an L. Whoops, my fault. All right. Well, anyway, why don't I just let Ken take it from here? Please welcome Ken. I'm butchering it. Thanks, Ken. Come on up and you explain it.
Freudian slip of some kind there. All right, so as Chuck mentioned, I'm sort of a recovering CAD guy, so haven't done CAD in quite a while, but I'm going to talk to you today about something a little bit different than CAD. So I'm going to talk a little bit about some ideas we've been playing around with in my group about merging biological components with solid-state electronics and sort of what the possibilities of that might be. So if we look at this is actually a slide that I've been using for a while. This is actually a slide from Intel from 2005, so it's interesting to see what they predicted would be like now. And they're actually not too bad. So basically, everything has been following this Moore's law scaling curve, as we know. And so that's been driving sort of all of CMOS as we've been talking about. But there's also a desire to sort of figure out what to do, what else to do, other than just trying to continue to drive Moore's law, which is obviously sort of starting to saturate now. And so there's been a lot of focus on heterogeneous integration, putting other materials and things onto the CMOS platform to give us other kinds of functionality. And so what I'm going to talk about today is sort of, and that palette has traditionally been sort of a palette that includes primarily solid-state materials and solid-state kinds of things. So piezoelectric materials, for example, or magnetic materials, which is what my company's doing. But there's a real opportunity to think about expanding that palette a little bit, and that's sort of what we're going to be talking about today. So, yes. So to put this in context, the solid-state world and the biological world tend to wring their hands and look at envy at the other. So if you look in the solid-state world, we tend to look at biological systems and we wring our hands and we go, oh man, if we only could create things that worked like biological systems, everything would be a lot better, right? Why do we make computers the way we make computers? We should make computers that emulate the brain. Why do we do whatever we do the way we do it? We should do it the way living systems do it. And it's a very sexy and attractive idea, and it's been around for a long time, 40 plus years or more, since sort of the advent of solid-state electronics. And, but it's had a lot of challenges. And the classic example is we don't make airplanes that flap their wings, right? And there's a very good reason for that. So they're very different technologically, what biological materials are and solid-state materials, and their capabilities are very different. And by definition, the way you design an optimal system will be very different. So one has to be very careful about these sorts of things. At the same time, if you look at the biological world, they're also wringing their hands together and going, oh God, if we could only be like the solid-state world, if we could only engineer things like the way they do microprocessors and things, everything would be much better. And so the whole synthetic biology community has sort of latched onto these ideas of trying to emulate the design techniques used in the design of solid-state systems. And so, we just need to make data sheets for components, biological components, and then we can just hook them together like you can components on a printed circuit board. Also, very, very attractive idea, but also very, very challenging. Because These components, first of all, they're not fundamentally well understood. You can't just hook them up the way you can hook up stuff. The interfaces aren't anywhere near as clean as they are in the electronics world. And this also is a very, very difficult idea. So one possibility is, why not try to put these two things together? And not try to make biological things act like solid state, not try to make solid state things act like biological. Just use the things for what they're good for and use the other things for what they're good for. So for example, I could take the best Intel designers and give them a $2 billion fab and ask them, design me a system that can tell me whether there's a skunk in this room or not. And they couldn't solve that problem, right? I could take the best synthetic biologists in the world and say, design me a system that couples to the electromagnetic spectrum. I'm not picky, anywhere between 1 megahertz and 50 gigahertz. They couldn't solve that problem either. The two technology platforms have fundamentally different capabilities that make them very good at doing certain problems and terrible at doing other problems. So for examples, if you look at solid-state systems, we have senses of sight and touch and smell and taste. Solid-state systems are able to do sight and touch pretty well. Piezoelectric materials, we can detect photons, we can detect mechanical energy. Energy we can detect from light. We can do electrochemical, we can do mechanical. We can't do biochemical very well. So there's capabilities that solid-state systems don't easily have that biological systems do. And so the idea is, how do you grapple onto those things? So if you look today at the way we interface biological systems in the solid-state world, 99% of the time, we use photons as an intermediary. If you ask a typical biologist, what are the two solid-state things that they care about the most? Well, first, they'd probably take a while to figure out what that meant. But after you explained it to them, they'd probably realize that it's the computer that they use to process the data. And there's a lot of the biological revolution that we're seeing today is being driven by the increase in computational capabilities that exist. The other thing that they would care about is their camera, the device that they use to convert light to electrons. And that's pretty much all they would care about, because they use light as the way to interact between the solid-state world and the biological world. It allows them to act at a distance. That is, they can send photons in relatively non-invasively into biological systems, and they can send them out. The challenge with light is it doesn't interact with most biological tissue well. That's its strength, but also its weakness. That is, you can't interact with biological processes very well intrinsically with light. So they've gotten really good at this. That's what the whole optogenetics is about. And they've managed to modify living systems in a way that they begin to interact with light in a natural way. But it allows them to both actuate and record from biological systems using light as an intermediary. And there's an enormous renaissance or amount of work that goes on in microscopy. So that's 99+% of what goes on is all using photons. The other 1% is electrophysiology, which is direct electrical connection between the biological system and the solid-state world. And this has also been around for a while. And here you're primarily looking at catching ions and the effects of ions. So biological systems use ions to carry charge, and we'll see a little bit more about that. And you convert those ions to electrons, and you can now interface directly with the biological system in this manner. The ways of doing this are often very tricky, and I'll show a few examples of it. But so one of the ways you can get to an ion channel in a cell, for example, is to come in with this little patch pipette that comes in and sticks onto the cell. And you can actually get just sort of single ion channels into this tiny little pipette, and you can measure these sorts of gating action of those channels. The electronics here, I might add, are generally very old. This is one amplifier. That's about a $15,000 thing that sits on a rack mount. That's sort of the state of the art today in electrophysiology. So if you want to look at I'm just going to briefly mention that solid-state electronics is already having an effect on these sorts of electrophysiological interfaces and electrochemical interfaces. These are just a couple of examples. Here we're talking about attaching to whole cells, and I'll go through these examples quickly. So here's an example where this is a chip from my group where we basically built an array of electrochemical sensors on a chip. We grow these biofilm colonies on the chip. These biofilms secrete these metabolites that they use to, among other things, they signal between the bacteria and allow them to organize themselves. And we can actually image these from this chip that this colony is sitting on. So we can temporally and spatially image what's going on. So here we're interfacing electrochemically between the biological system and the IC. That electrophysiology thing that I showed you before with a single amplifier the size of a rack, well, you can make chips where you can put 65,000 of these on a chip, right? So that allows you to do all kinds of interesting things. So this is one example where we're recording from a retina by placing a retina directly on this chip. And here we're recording the activity of ion channels in the excitable neurons that are producing extracellular potentials that are measured from the IC. These interfaces get even more elaborate. This is an example of a collaboration we're doing with Caltech. These are for in vivo experiments. These are little electrodes that are on these little needles that get stuck into the brain. And these are brought out to a set of chips that are on a stack of boards that's about the quarter of the size of a credit card in extent. And these have, again, dense CMOS amplifiers to amplify the electrophysiological signals. And these are examples of some of the recordings that you can get from these things. So what you're looking at here are actually action potentials from neurons that are in very close proximity to these electrodes that are running down the shanks here. Okay. So all of these extracellular things that we are measuring are happening because the cells contain channel proteins. So these cells consist of membranes, and these membranes have within them these embedded proteins. These embedded proteins are things like transporters, which can transport things. So in the case of the electrochemical activity of the biofilm, those transporters are pushing out these metabolites, these signaling molecules that we're detecting. Or they can be ion channels that open and close, resulting in the flow of ions, the flow of charge, and electric potential that we can record, which is in the case of the electrophysiology. So instead of carrying around this whole cell, the idea is, can we think of ways of interfacing to these biological components, these membrane protein systems as a component, analyze it electrically, and interface to it from the solid state world. That's sort of the idea. Now these channels contain a tremendous richness of function. They're what give biological systems their ability to sense all of the energetics, all of the signaling. All of this happens through ion channels. In fact, 99.9% of drugs are associated with acting on these channel proteins. They're so fundamental to living systems. And so the joke is departments of pharmacologies are often called departments of ion channels because all they care about are ion channels. They're the thing that drugs act on. So we started playing around with this stuff by trying to interface between single ion channels and solid-state electronics. So we started by doing this by building little tethers where we actually put little wells where we suspend these membranes, these lipid bilayer membranes. So we create an artificial cell membrane, if you will, and embed one of these channels in that membrane directly on the amplifier of an IC. And what this allows us to do is directly measure the activity of this channel through this amplifier that's underneath it. The advantage that this very close integration gives us is that we can reduce the parasitic. So before, the way one generally does this is one would have a patch pipette. Again, that little glass thing that I showed you, patching something. You would go out to this external amplifier here, and the total amount of capacitance you would have on this would be on the order of maybe 50 to 60 puffs. The amount of current that this channel is producing when it opens and closes is on the order of tens of picoamps. So by having just tens of picoamps of signal and going into about 50 puffs of capacitor, the bandwidth that you can do that measurement is extremely limited because you're basically, excuse my French, pissing away the signal with this very large capacitance. So what we were able to do with these systems is reduce that capacitance dramatically to cases where it's a puff or less. And that allows us to push the bandwidths up so that we can do these measurements. And we're actually measuring now these ryanodine channels, which are very important channels for the heart, cardiac channels, and we're able to measure them now up to bandwidths of about 500 kilohertz, which is more than a factor of 5 beyond what anyone is able to do today through these kinds of integrations. So here's some examples of some of these measurements that you can do. So this is the opening and closing of one of these channels, and we can see very, very fast dynamics. I'm sorry this slide has way too much crap on it, but you can see some of the very fast sub-microsecond scale dynamics in some cases that we can start to see with these kinds of interfaces between these artificial ion channels. I mean, these channels in these artificial membrane systems interface directly with solid state. So we wanted to think about sort of taking this to the next level. So could we imagine creating hybrid engineered systems that combine functionality of biological systems in the form of ion channels and mate these to the capabilities of solid state? So ion channels are basically transistor-like in functionality. They exist, they're like little switches that exist in a membrane that acts like a capacitor. So that's sort of what I drew here, where you're actually storing charge across that membrane in the form of ions. And so they work and they act a lot like transistors. And in fact, you can think of them as transistors in their functionality. So can we imagine creating sort of hybrid systems that contain these things and exploit them in new and interesting ways? So I'm going to talk a little bit about that. Sorry for this is a little bit technical probably for a keynote, but bear with me. So what I've drawn here is I've drawn sort of two reservoirs, and I've drawn a membrane that exists between these two reservoirs. And on one side, I've got a salt solution of sodium chloride, and well, I have sodium chloride and potassium chloride on both sides. And I have different concentrations. And so I have different concentrations, in particular, of sodium potassium ions on either side of this membrane. And then I have channels here that are permeable only to potassium ions or sodium ions. And then what happens is if there's a gradient in the ions across this particular interface, what happens is I get basically a built-in potential that develops. So this analysis is completely analogous to solid-state physics, where we study electrons in holes as two charge carriers, and we have expressions that look almost identical to this that are related to the built-in voltage, for example, in a p-n junction. Where we create a p-n junction, we get drift and diffusion. Exactly the same thing goes on here. It's exactly the same physics, absolutely the same. The only difference is the charge carriers here are ions, they're not electrons. And so you can draw an electrical picture for this circuit that looks like this. You have the capacitance of the membrane. You have these built-in voltages, if you will, associated with these what are called Nernst potentials that exist. And then you have these resistors that are in series with those that are related to the conductance of these channels. And so you can build basically a very, very simple kind of circuit model here. And this has been around, this is the basis of Hodgkin-Huxley, the Hodgkin-Huxley model for excitable cells. And this has been around, these ideas have been around for a while. So if you solve that circuit, you can actually solve for the actual potential that exists across the membrane just by solving this electrically. And what you find is these membrane potentials, for typical concentrations, physiological conditions in cells, can be on the order of 50, 60, 70 millivolts or so. So one key point to note in these things is that these potentials that exist that these channels operate at are much lower in general than the potentials that transistors operate at. And that's going to be one of the fundamental mismatches that we're going to have to deal with in these systems. And the reason for that is that these ion channels function mechanically. They don't rely on transport over a barrier, which is the way we operate in the solid state world. So we need to, in order to switch a transistor, we need a few kT over Q to basically raise and lower a barrier height by enough kT over Qs to sort of cut off a Maxwell-Boltzmann thermal distribution. That is not the way these channels work. These channels all work by conformational changes, so they can operate at much lower potentials. Yes. Okay, there we go. Oops. Okay, so actually, this figure also had, oops. Boy, everything is, okay. There's a lag. What I also showed here is the action of pumps. So one of the other things that we're going to be playing around with here are actually these ion pumps. These are actually very special kinds of channels. What they do is they extract an energy source, and they use it to, in our case, it's going to be ATP, and they use it to actually move ions across a gradient. And those can be modeled as very simple current sources in this kind of thing. And it's those ion pumps that actually give you the energy in the system, that allow, for example, neurons to have a resting potential. That happens because there are sodium-potassium ion pumps that are actually operating, hydrolyzing ATP, and pumping ions. So here's an example of what one of these pumps looks like. So this is actually the pump that we're going to be using for the examples that I'm going to show you that we played around with. So what these do is it hydrolyzes ATP. This produces some energy. And it uses that to basically pump 3 sodium ions one direction and 2 potassium ions in the other direction. And the net result of this is there's a net movement of charge across the membrane, which is actually what we're going to exploit in the examples that I'm going to show you in a few minutes. So these are examples of what are called electrogenic pumps because they actually move a net amount of charge across the membrane. So if you look at the way the system works is the pump pumps sodium and it pumps potassium. It has a net amount of charge that's moved, so there's a net current that flows here, which is what I've shown here. This is Q, this is the number of pumps, this is the rate of turnover, how many ATP molecules are being consumed and ions being pumped. So this whole thing has units of current. This is the membrane capacitance again. This is the Nernst model that I had from before. So I can now write an equation for the membrane potential here that looks like the following. And this is the same expression that we had before, but I've added this extra term over here, which is the action of the ion pumps directly. Let me comment on 2 things. So the ion pumps have 2 actions here. They're directly adding to the membrane potential over here, but they're also acting to create, in effect, these 2 Nernst potentials here, because the atoms that they pump, the ions that they pump, are actually the ions that are producing the gradients that are giving us these Nernst potentials. So all of that's got to factor into the energetics. Now, in most physiological systems, that is, in most living systems, this resistance here is relatively small, so this term is actually negligible. So most of the membrane potential comes from this Nernst potential. And in fact, in many biology textbooks, they ignore this altogether. You have to really dig into the biology literature for people to even talk about this at all. In our case, it's going to be just the opposite. This term is going to be negligible because we have relatively large reservoirs. There's very little ion gradient. And all of the energy that we're going to be exploiting is actually coming from this term over here. So we're actually going to be putting these together. I should have probably said that up front. We're going to be putting these pumps together with solid-state systems to power the solid-state systems from these pumps as an energy source. OK. So again, here's the picture. I've said all this already, so I can go through this slide very quickly. So these are the 2 components of this membrane potential. This ohmic potential, which is the direct action of this pump, this electrogenic pump, on these resistances, plus the action of these 2 voltage sources. So just very, very simple circuit analysis that drives the way this thing is going to operate. And again, for our case, this term will dominate. In biological systems, this term generally dominates. So how do you do this? I mean, how the hell do you get these pumps to sit on there? Now, it's actually a real pain in the ass, which we didn't really realize when we got into this thing, that this is a very, very tricky business. So so the lipid bilayer membranes you form here. We've been using what are called DOPC lipids, and they form naturally into several different kinds of configurations. These things called liposomes, where there's actually a little a hole here in the middle of this sphere. Micelles, which have no hole in the middle, and then bilayer sheets. You can form these things in a few different ways, and we actually tried several of these different ways of getting bilayers onto chips. The first way is to what's called supported. So what you do is you take your chip, you form some sort of a hydrophilic surface. So we used SiO2 here. And then you actually just sort of suspend, or rather support the bilayer on top of this SiO2 surface. Now in our case, we had to make the surface porous here so that we could get to an underlying electrode. At least this is what we tried to do. And here's sort of an example of what one of these porous surfaces look like. And we tried to fabricate this, and it didn't work very well. We wound up getting very, very low yield. as we'll see later, we need to get the resistance of this membrane. This membrane can't be leaky at all for this to work. So these ion pumps are generating relatively small currents. And so if our membrane leaks, we're basically going to get rid of all the energy. I mean, we're going to leak away all the energy that we're creating. So the membranes have to be very, very high resistance, have very little permeability to ions at all intrinsically, so that we can get the full benefit of these channels. And it turns out that these supported membranes were never good enough for what we wanted to do. We could never get them to have a low enough membrane or high enough membrane resistance. They were always way, way, way too leaky. So we went and we said, OK, let's try something else. Let's do basically what we had done, I showed you before with the ion channels, when we measured the ion channels, which is to create what is called a suspended membrane. So we form this you can form a little well here, and you can suspend a membrane. Here, this is a hydrophobic. You can use SU8, for example. And you can suspend a membrane here rather than support it. And you can put channels in here. And this is what we did to do the single ion channel measurements that I showed you before. The challenge that we have in this case is that we actually need to have a relatively large area for this thing, so that we can get a relatively large number of ATPases, or these ion pumps, into that membrane to get enough energy to power our system. And so you can think of this as like these lipid bilayers are like a soap bubble. So you imagine like when you were a kid, you pick up the little ring and you stick it into the bubble stuff and you pull it out, right? And it's coating the ring. That's exactly what's going on here. And so these membranes can pop, like a bubble can pop. And so part of the challenge of these things is to form these membranes. And obviously, the bigger we make the ring, the more unstable that membrane is going to be, and the easier it's going to be to pop. So we had to find a way of making that opening big enough that we could get enough ATPases in there to get enough energy, but not so big that the membrane became unstable, that we could keep that membrane alive for a long enough time, in order to do the experiment that we needed to do. So you can see why this is very, very tricky stuff. So here's what we did before on that. But in this case, we couldn't do that. So we used a Teflon ring instead. So it literally is almost like you can think of it like that bubble ring, when you make bubbles as a kid. A little bit more sophisticated than that. And so this little package sat on top of our chip. And for reasons that I'll say in a little bit, we had to actually stack two of these membranes together. And the reason for that is each one of these membranes gave us about 80 millivolts of potential. But we needed 145 or so in order to start our circuit up because of the KT over Q limitation of solid-state electronics. So we had to stack two of these to give us enough potential in order to do that, which made the problem even harder because we now had to get not only one membrane to work, but two membranes to work in a stack. But what was nice about these membranes is the resistance of this membrane was about 300 gigohms. Okay? The membrane capacitance here was about 150 picofarads. And here's actually the characterization that we did of both that membrane resistance and this membrane capacitance. Now, one of the things that you've got to keep in mind when we're talking about impedances that are this large is that it's not trivial to do electronics that interface to systems that are of such high impedance. And so one of the big challenges that we had to have in all of these experiments is to deal with these very, very significant impedance mismatches between the very, very high impedances that we're dealing with and very, very low currents that we're dealing with in these biological systems with the relatively lower impedances that we're dealing with in the solid-state world. And interfacing those was another important challenge. So we had this voltage mismatch, and we have this impedance mismatch that we have to contend with. So these are actually characterizations of both of these things that we did on these membranes. OK, so now how do you get the pumps into these membranes? So, the simple channels that I had, some simple channels get in by self-assembly. That is, you just stick them in, they find their way into the membrane, and you're done. But unfortunately, any channels that are interesting don't work that way. So to get them into the membrane is a little bit tricky. And it's a lot of black art, and I'll say a little bit about it. But basically, the first thing we're going to do is we get them into these proteoliposomes. And then when which you can think of as little soap bubbles, these little soap bubbles then land on the membrane, and then they naturally fuse into the membrane. Well, not naturally. You have to create the right conditions for that to happen. And then once that happens, then you can get the membrane, you can get these proteins into the membrane. And so that's what we had to do. So we had to get these membranes suspended onto these little Teflon rings, get these proteoliposomes in, get them to fuse with the membrane, get the proteins into the membrane. So I won't spare you with the details, but basically the way you get the proteins in these proteoliposomes is you have to go in with detergent, surfactants. So exactly like the way you do your dishes at night, to break up the grease, right, the lipids, you go in with detergent. The problem here is we need to break the lipids enough that we can create an opening to get the protein in, but not break them enough that they all come apart. So you have to find just the right amount of surfactant to get in there to make openings that you can get the proteins to go in, and then you got to pull the detergent out. Otherwise, it'll kill your system. And so that's basically what this protocol is all about. And it's a very tricky undertaking. But if you're lucky and you say the right magic words and you do the right incantations, you get proteins that are in these proteoliposomes. So here's a little bit about how this works. So we did that. So we got these ATPases, these purified sodium-potassium ATPases that hydrolyze ATP, pump ions, exactly the same kind of ATPases that exist in neurons that create the action potential in neurons. We stacked 2 of these on top of each other to get this, and this is some of the measurements that we did here. So what this is showing you here is this is the short circuit current, and this is the open circuited voltage. And so basically what happens is you basically get, once you enable this thing, right, you start drawing a current through this current source. That's basically the action of the pumps. And then this reaches a steady state potential here, charging up the membrane capacitance, and you reach the steady state resting potential. This is actually just one membrane, so this is 80 millivolts or so. So this is a single bilayer membrane. And again, these measurements here were extremely, extremely difficult to do. So in fact, for example, the input impedance of this custom amplifier that we built here was about 10 teraohm in order to do this measurement. So we're talking about a 300 gigaohm membrane, so we needed a 10 teraohm amplifier to measure it. This is what happens. So this is the IV characteristics of this particular system when there's no ATP. So you just have basically the membrane resistance. Again, that 300 gigohms. I now go in, I stick ATP in the system, and voila, this is what the IV characteristic looks like. Looks a lot like a solar cell, right? Basically, you move down here into the 4th quadrant, which means we are generating energy. And so suddenly now we can, if we bias somewhere in this region here, we're actually going to be pulling energy out of this membrane system by action of its ion pumps. In fact, this measurement we searched the literature. No one really characterized this at all for ion pumps. This is sort of one of the first times that anyone has really sort of characterized ion pumps in this kind of a way and thought of it in this kind of a way. So you can build very basic circuit models for this thing. So actually this thing acts like a nonlinear current source, so you can model it that way. You can also linearize it, as is sort of done here by modeling this as it's sort of like a straight line, and it has a certain resistance associated with it, which I call RP. So to give you an idea of the relative magnitudes of these things, RM here in our system was about 280 gigaohms. RP here is about 61.6 gigaohms. And this current source here is about 1.8 picoamps. So the total power that's being generated by this biocell was about 163 femtowatts of power. Okay? So that gives you an idea here. We're not talking about picowatts anymore. We're talking about tenths of a picowatt of power being generated by these cells. Okay. So how do you make a chip to interface to this? Let me go through this relatively quickly. So we've got the basic cell, biocell, that this little ATP thing that I mentioned to you before. It has a running at a voltage of about 80 millivolts, excuse me. It has an input power of about 163 femtowatts. To get a transistor to work, we need about 125 milliwatts. And to start this thing up, we wound up needing about 145 millivolts, excuse me. So what we wound up having to do is to stack 2 of these cells together. So we also needed to be extremely careful that we didn't throw any power away. So everything is extremely leakage aware. I mean, in a way that's beyond anything that one normally worries about in any sane world, where you have a power source that's a little bit more than 163 femtowatts. But at 163 femtowatts, you don't got a lot of space to throw stuff away. So it was a real challenge to sort of get all the pieces in place. We didn't try to do a hell of a lot here. We don't have a hell of a lot of power. So the first thing we did is we actually double up the voltage to give us a little bit more room to play with. So we double that up. So the first thing we've got here is a voltage doubler. And then we literally run a bunch of ring oscillators as our loads, and that's sort of what we did. So you'll see some data where we actually show these ring oscillators turning on, and that was sort of the nature of the circuit. What's interesting is you've got the usual cat and mouse game here, where we've got a voltage doubler that relies on a clock, and we've got a clock that relies on the output of a voltage doubler. So we got this whole thing to start up, self-start up, without any tricks at about 145 millivolts. So the system I'm going to show you will start up directly from the stacked biocells. So no tricks, no external potential coming in, doing anything. OK, I can skip over some of this stuff. These are the ring oscillators. I will skip over this. So here's the big picture. So there's one other external circuit piece that we have to add here, and I'll say a little more about that. So here's the biocell again. So we've got the action of the pumps. We've got these resistances here. This is the resistance associated with the pump model. This is the resistance of the membrane. This is the capacitance of the membrane. These are parasitic resistances associated with the electrochemical interface between the cell and the chip. Now, the other thing we've contending with here is we've got an enormous impedance mismatch between these two systems. So we've got something over here that's consuming nanowatts of power. We have something over here that's generating sub-picowatts of power. So the way we manage that is with a capacitor. So a capacitor and a switch, effectively. And this capacitor charges up, and then once it's reached once it's charged up, then we transfer that power to the load. And we have to do that with very heavy duty cycling. So the way to contend with this so that duty cycling was about a million. So we would integrate up everything for, yes, that's correct, 6250 seconds, and then we would run it for 5.5 milliseconds. Okay? So it's crazy. But this is the challenge you've got. So we really had to push a lot of things here to try to get this to work. So we've got real serious mismatches between these two systems. Now, we could have improved things a little bit. This could have been a little lower power. There could have been some things that we could have done here to improve things a little bit. But in general, that's the way this is going to work. When you're dealing with these kinds of, when you're trying to mate solid-state systems, which fundamentally use a lot more power from these sort of very low power biological sources, the only way to handle that mismatch is with heavy duty cycling. So you basically go to sleep for a long period of time, you wake up, you do something very quickly, you go back to sleep. So I'm going to quickly go through some of the results here before I run out of time. So here is showing you what happens after we build up about 145 millivolts from the two stacked cells. We close this switch, and this is the voltage doubler starting up. This is the output of the voltage doubler, and these are the little ring oscillators that are operating. And then once you charge, you discharge the capacitor. This stops. We close the switch again. We go to sleep for another 6250 seconds, and then turn it on again. So, but this chip is running from power that was harvested from this biocell. Other interesting things, the efficiencies and so the maximum power transfer occurs we all learned from kindergarten circuits, occurs when this load resistance matches this impedance here, right? Unfortunately, that's not the most efficient, the place of most efficient operation of this system. So that's not the point of maximum efficiency. So I'll spare some of the details here, but you can actually go through and figure out what's happening here. And so Every time you hydrolyze an ATPase, you release this, you take a certain amount of energy to do that. For that energy, you basically get to pump one net charge across this pump. And so if you do all that analysis, taking into account the actual energy that's being consumed by the ATPases here, you wind up with an efficiency for the biocell itself that it's optimized at a different value of the impedance of the load that winds up being about 14 or 15% here for this system. Now, I'm going to come back to this in a second. If biological systems operated at 15% efficiency for ATP, we would all be in big trouble. That gets back to what I said before with the Nernst potential and the electrogenic. So what's actually happening is for biological systems, we are not harvesting the Nernst potentials that are being produced here at all. And biological systems, when you take that into account, which I have one quick slide on that, this number would be about 95% for biological systems. So biological systems, evolution does a great job in fixing things, and it got us to about 95% efficiency. So because of the way we're operating this thing, we're much, much lower efficiency than the way biological systems operate. So here's the efficiency of the whole system. We'll lose some in the converter. So the overall system was about 8.8% efficient in taking energy from ATP and converting into final action in the solid state system. So not bad for a first attempt. So I'm going to cut through the chase here. This is way too much detail. But the only point I wanted to make here is the point I made already, which is that biological systems do a much better job at this, which is they more fully extract the energy that the ATP is actually producing here. And that is through the action of these Nernst potentials. And so if you actually go through this analysis for, say, a squid axon, you wind up with about 95% of energy efficiency in the way that biological system operates. But that requires a lot more complexity in the engineered system than we've been able to do in this very simple demonstration. Okay. So what can you do with this thing? So there's some intriguing ideas that we're playing around with. One is artificial organelles that could actually sit inside of cells and be powered by ATP. So ATP is not something that is flying around. It's not in your bloodstream. It's actually inside of cells, not anywhere externally. It's part of the energy machinery inside of a cell. So this is a cell that we're playing around with some collaborators. This is actually an algae cell that's, this is 500 microns here. So these algae cells can get quite large. This algae cell is almost 1 millimeter in diameter. And these are actually important because these algae cells are forming huge blooms in the Indian Ocean and killing off fish. These things are really crazy. If you actually look inside them, in their cytoplasm, they actually have other symbiotic cells that sit inside these cells. So it's a symbiote. So this big cell has little cells inside of it. And they're very curious about this intracellular environment. So one of the things we're playing around with is getting sort of implantable systems that can go inside of these very large cells. So that's one possibility. But a more interesting possibility is to sort of think about other kinds of applications. So there's ion channels can do an awful lot. I mean, we just did powering, but that's may not even be the best place to go. So ion channels are basically responsible for all the senses of taste and smell, all the ligand sensitivities. So there are ion channels that are ligand-gated ion channels, and they basically gate by the action of the presence or absence of a molecule. So this transistor will turn on and off depending on whether there's a molecule present or not. So if we can exploit these kinds of molecules and engineer them in some way, we could create systems that solid-state systems that could actually really detect do molecular recognition in the same way that biological systems do. So these are some examples of ligand-gated channels. This is one that we've started to look at. It's an olfactory receptor of an insect. I mean, the real dream, of course, though, would be to do it the way your nose does it. And that's a much more complex proposition. I'm just going to put this up, and then I'll end. The way we do it is with what are called GPCRs, G-protein coupled receptors. That's how the mammalian nose works. And so those drug-sifting dogs, they work so well because there is a wealth of these G-protein receptors that exist that allow the dog to detect an enormous constellation of molecules, from odorants to hormones to neurotransmitters, and in some cases engineered to respond to light. But these don't work in a simple way. So here's one of these gated channels here. This is actually the ion channel. But this operates in a much more complicated way. So the odorant comes in, it activates this protein complex. This comes over here, interacts with this adenyl cyclase. That produces the CAMP molecule, which then comes over here and opens up the channel. So there's a much more complex signaling cascade that happens here. Why do living systems make it more complicated? You think, why would they do this? Why would they make this more complicated? Because there's an opportunity to get gain here, right? One molecule in, many molecules out. So the reason why living systems do it this way is because they intrinsically get gain in the system by doing so. They don't have amplifiers to amplify things up, right? So biological systems evolved to do this all chemically through, and that's why this more complicated system develops. The challenge that creates for us in exploiting this is if we want to exploit this directly, we have a much more complicated system that we have to get to work in an in vitro environment, which is not easy. Another approach would be to modify these ligand-gated channels directly to do the detection, which is what I was showing in the beginning, and then relying on the electronics to give me the gain, right? So use the CMOS to give me the gain and try to take it out of the biological, but still use the machinery of the biological for the molecular recognition part. And this gets into this whole interplay that's naturally going to have to come up between engineering the biological part of this and engineering the solid state part of this, and where's the place to make the right trade-off, given that we're building now a completely different kind of system that has different capabilities than either the solid state had by itself or the biological had by itself. Okay, so to conclude, so the thesis here is that the future of bioelectronics is going beyond traditional cell interfaces, the stuff that we all have been doing up till now, and trying to build systems that don't carry along the whole cell for the ride. Cells are complicated things. They want to do a lot of stuff. They want to reproduce. They're doing lots of stuff, right? And we may only care about one particular function of the cell. Can we sort of pull out that function biochemically and exploit it? And I've tried to show one example of that in this energy harvesting example. Oops. So this idea of hybrid biological systems promises sort of a broad range of new capabilities if we can actually harvest these components and use them. But this comes with an enormous number of challenges, obviously, and I tried to get a little bit of a flavor for that here. But it creates really opportunities to engineer both the biological and the solid states synergistically, to really combine ideas of synthetic biology and what we do already to create unique capabilities. And so I think this is really an interesting new area to start thinking about that's sort of beyond where we are today. So I want to acknowledge the work this is primarily work done by two of my graduate students and one of my postdocs. Jacob right now is a professor at Brown. He's left my group already. And this was primarily funded by ONR and the Keck Foundation, which funds stuff that's really weird that NIH would never touch. And this certainly fits in that category. So I'm happy to answer any questions. It's 10 o'clock exactly. Just in case you're checking.
You used up all the time perfectly well. So,
all right.
And we do have training day starting in 15 minutes. So,
okay.
But are you willing to stay up for questions after?
I'd be happy to.
Okay, so just come on up and we'll take questions after. Now, we had this special plaque made for the other keynote speaker, but I got a Sharpie and wrote your name on it. So anyway, maybe we can make you a new one, but I thought maybe you'd appreciate it this way, because it kind of tells a story behind it. Yeah, so I appreciate it. Thanks so much for pitching in.
Okay, no problem.
Appreciate it. All right, look at the camera for a second. Okay. Thanks so much, Dan. All right.